This is pure maths, paper 1 from 2019. Let's just do it. So factor theorem then, if x plus 3 is a factor, that means f of minus 3, just swap that over, is equal to 0. So okay, put minus 3 into all of these x's here. Minus 3 cubed is minus 27, minus 3 squared is positive 9, just be careful, two negatives here make positive as well. We get this, we do some solving, and we just end up with a as 3. Good. Question number 2 then. So we've got this equation here, which is kind of interesting. We've got the cos graph drawn here for us. Now, what we can do is we can rearrange this to have just cos on its own. So cos of x equals these things here. And what this means is these two things are equivalent, of course. What we can do is we can look at this one and we can say what it's really saying is where does the graph cos of x intersect the graph 2x plus a half? We've already got the graph cos of x. And even better, actually, we know that cos of x has a minimum of pi. And pi is just bigger than 3, right? Which implies that this is just a box of 1 across and 1 across and 1 across to get you to just over 3 here. And of course, cos has a maximum of 1, so this is just a 1 by 1 box, which makes drawing this line super easy, right? It has a y-intercept of a half, which is like here, and then a gradient of 2, so it goes across 1 up 2 when we get to there. And it ends up looking a bit like this. And we can see clearly there's only one section here, which means there's only one intersection to this, and therefore only one solution to that. And you have to write something a bit down a bit like that. Small angular approximations are in the formula book. Here they are. So cos is this one. So we're going to replace this cos here with this and just with an x there, obviously. Going to double this and stuff, and we get this. And then our calculus will give us some answers. That is here. And now we've already argued that this only has one solution. It's this one here, which is a positive number. It's just to the left, sorry, to the right of the y-axis. So which one of these is positive? Well, clearly it's minus 2 plus root 5. So that'll be the answer as a decimal is this. The reason the other one exists is because, of course, when you do use this approximation here, this is an upside down quadratic, and it just pretends the graph continues like this, and there'll be another intersection down here somewhere. But we, of course, ignore that because cos doesn't do this forever, and we get this here. That's the only solution. Now, I've talked about how much I hate quotient rule in the past, and I really do hate it. But for this particular example, I'm going to go back on everything I said and say that it's probably easier to just use quotient rule here. It's in the formula book, right? Just call this g of x and call this f of x. And then what we're told to do is square the bottom thing. So this becomes x plus 1 squared all squared. And then differentiate this f first to make this and just put this g next to it. And then take away, apparently, just leave this one alone. And then put this one here differentiated to finish up. This differentiates to 2 down here. This goes to a 1, and then the derivative of that is just 1 anyway, so it goes away. Now something quite useful happens, which is why quotient rule is probably the way to go. This cancels with one of these, and so does one of those. So we end up with this, which we can just expand out, and then lots of things cancel, and that was probably the fastest way of getting it done, rather than using a product rule with a negative power, even though that's what I do 99% of the time. Anyway, hence deduce the range of values that this happens, so I want this to be less than 0. Now, 10 divided by something has to be less than 0. The only way to make that is to do 10 divided by some negative number, right? 10 divided by anything positive isn't going to be less than 0. So we just need this thing to be negative. A positive divided by a negative is a negative. So we just need that to be negative. Cubes are really nice because positives cube positives and negatives cube negatives. So we just need this to be negative if we want its cube to be. And then we just take away one from both sides and we end up with our answer here, which we'll accept. 4 then is binomial expansion, so it tells you this in the formula book. This is how you do a binomial expansion when n is not a integer. Of course, we can write this as to the power minus a half, and then this doesn't quite match up with this. So I just need to factorize out 4 from this. And of course, when you factorize out 4, you need to keep this power as it is, so you need to match these powers. And then, of course, 4 to the power minus a half is the root of 4, which is 2 flipped over, which is a half. And now we're ready to expand this using this formula here. So we start with a 1. Obviously, the half is just on the outside. But we start with a 1, and then it's nx. So we've got n is minus a half, and x is minus a quarter x, according to our formula. So it's n there, minus a quarter x there. And then you just do a half x times, sorry, you do minus half times minus half minus 1 over 1 times 2. And then again, x, which is actually minus a quarter x, all squared here. And those are the first 3 terms. No, sorry, yeah, 3 terms, which is all it asks me to do. Put in a calculator most of this stuff, and you get this, and then you can halve everything, and you get that. And that'll do. The expansion can be used to approximate root 2. So if you put in x is equal to minus 14, then that becomes 18, and 18 is the same, I think, as like 3 root 2. And then you rationalize it, and you end up with this here. Now, the reason that doesn't work, and this is the first question here, this doesn't work because if you put minus 14 into here, or actually, let's look at this one here, because you've got this condition at the end of this formula here, which is that the size of x has to be less than 1. Now remember, Rx, when we were expanding this, was minus a quarter x. So basically, minus a quarter x has to be less than 1 or greater than minus 1, right, the size of it. But if you put minus 14 into this, you get something bigger than 1. So that doesn't work. So we just can't do this because it doesn't obey this condition of the formula. Essentially, minus x over 4, or the mod of x over 4 is greater than 1 if you use that. So we can't do that. Now, which of the other two is better? Now, both of the other two are fine with this, right? Because minus a quarter times 2 is minus a half, which has a modulus of less than 1. And of course, minus a half also works and makes an eighth. So both these work. The best one will always be the one that's nearest to 0. So this will be the best one here. The reason that is because you've ignored terms here when you're doing your expansion. And of course, you're ignoring terms that are like x cubed and x to the 4 and x to the 5. The smaller your original x is, the less those terms matter. Like minus a half cubed is already like minus an eighth, and that's making the numbers even smaller, whereas this makes the number bigger. And so if you're using this, these terms would matter more. So always try and use something as close to 0 as you can, and the approximation is as accurate as early as possible. And yeah, that's something like that will be good. F of x right in that form, so I just factorize out the 2 from the first two terms only, just ignore the 9. Then complete the square on this bit, so halve this number and take away its square. So halve that for a 1, take away 1 squared, which is just 1. And then expand the 2 out to both of these things to get this, and then just combine the 2 and the 9. And we get that. Sketch it, so it has a minimum of minus 1, 7, which is up here somewhere. And it has a y-intercept of 9, which is there. And then we can just draw a terrible curve through both, and we'll get all the marks. Next, describe the transformation here. Now, you could do something really intelligent here and look at this and think about how to get a graph transformation to go from here to here or from here to here. I didn't do any of those things. I did this in the dumbest way possible, which is just expand this all out and collect everything together. So here's just me expanding this and collecting and making a quadratic. And then I decided from here to do exactly what I had done here and complete the square. So factorize out 2 from the first 2, complete the square on the middle bracket there, expand the 2 back out, collect together, and you end up with this. Why is this helpful? Well, this tells me it has a minimum point at 1, minus 1, down here. And so all that's happened is this graph has been moved down, 8 from 7 to minus 1, and to the right 2. And I just wrote that. That was my translation. Down 8 and right 2. That is right, isn't it? Yeah. Cool. Find the range of this function here. So this function is the one that this should not have turned up. That's a spoiler. That's the answer, I guess. It should have turned up at the end. This function is the one we looked at before. It has a minimum value of 7, and then it can, of course, go to infinity. So when we're looking at this, the largest we can possibly divide by is infinity, which is going to make h of x like 0, right? 21 over a really, really big number just goes to 0. The smallest thing we can divide by is 7, because that's the smallest thing the function can be. And of course, if we divide by the smallest thing, we make the biggest number. So if we divide by 7, we get 21 over 7 is 3. And that's the biggest this can ever be, because we're dividing by the smallest thing possible. So h of x is definitely bounded by 3 from above. It can be 3 because we can make this 7, and 21 over 7 is 3. And then as we put in other things, as this becomes bigger, we just make something smaller and smaller, and we go towards 0, which will never actually be up because we can't put in infinity. But we will stop at 0, and we'll get something a bit like this. Cool. Question 6 then. So I would highly recommend you just memorize that sine 2 theta is 2 sine x cos x, or theta or whatever. It just saves you a lot of time if you just know that and can write it down. So we're going to fill that into here, which makes this. Tan, of course, is sine over cos, times both sides by cos, so you get this. And then we can cancel out these sine thetas. The only thing to be careful of is if sine theta is 0, then you're going to divide by 0, and that's a problem. Except, if sine theta was 0, we just have 10 times 0 times cos squared equals 9 times 0, which totally checks out because you just end up with 0 equals 0. So sine theta equals 0 is a solution here. And we can get rid of it as long as we recognize there's a solution there, which gives us theta is, I think, minus 180, 0, and 180, right? If you just imagine the sine graph. It starts at 0, it goes up, and then down to 0 again at 180, and the same thing on the other side. So we get those 3 solutions, and now we're looking for some solutions of this. Divide by 10, square root, Of course, when you square it, you end up with a plus and a minus. We will do these separately, do cos inverse of this to get this, and do cos inverse of this to get this in the calculator. And now we just need to look for any other solutions. Now, if we draw the cos graph between minus 180 and 180, we get this. This is like root 0.9, which is quite a big number. It's quite close to 1. So we're looking for intersections with this line here. And of course, the calculator gave us 18.4, but there's also minus 18.4. And likewise for this one down here, minus root 0.9. There's a solution here of 161. There's also a solution there of minus 161. And so we have 1, 2, 3, 4, 5, 6, 7 solutions. Now, to use the smallest positive solution to this, now all they've done here is they've replaced theta with x minus 25. So I think I can write x is theta plus 25, right? Just saying theta is this, and then just add 25 to both sides. Double check that works here, right? Is 2 theta equal to this? Or 2, if you times all this by 2, you get 2x is 2 theta plus 50. Take away the 50, and yeah, it works fine. So this is the correct thing. Now, we're looking for the smallest positive solution to this. So we run through all of our theta solutions, and we find which one would give us the smallest positive number here if we put it in. Now, if we put that in, that's the smallest number we have, right? Minus 180. But if we put it in, we get a negative, and we want a positive. But if we put this one in here, this minus 18.4, we're going to get quite a small positive solution. Smaller than if we put anything else in. So I think that will be the answer there. 7 then, so its value and u, so t is 0, v is this, and then here t is 1, v is that. We can put those into our formula now. If you're using an exponential model, that's v equals a e to the kt, something like this. That's an exponential model. You need a constant here, because when t is 0, that will essentially be the starting value. And you need a constant up here, because that tells you the rate of growth, because it's not necessarily e, even though e is the best number ever. That's not necessarily the rate of growth all the time. So we need a k in here as well. And that's why they've given us two conditions, because we can use them both. Like I already said, if you put in t as 0, this just goes away, and you just end up with a as v, so that's that. If you put in t as 1, a little bit more complicated. You can use the a now, but putting in t as 1 just gives you e to the k here. Putting in v as this, you can divide by 20,000, and then you can take log of both sides. Or, that's actually not what I did. I decided I couldn't be bothered to do that for some reason. I can't remember why. But you can write this as e to the k or to the t, because of course those two things would just times together to make this. And e to the k you've just worked out as 0.8, so now I can write it like this and just remove the e entirely. I don't know why I did that. Sure, but it's it's a legit answer. It's fine. But most of the time, just do log or ln 0.8 to work out k, and then you can just put the k in here. But this is kind of neater because it doesn't involve a nasty decimal. So yeah, maybe that's why I did it. Anyway, the value of car is monitored. After 10 years, it's worth this. Put 10 into this, and we get quite a close answer, I think. We get this, which isn't very far off, so it's pretty good. And then the following information is available for B. It has the same value when new as car A. Now, that means if you were going to model it, A would still have to be this, because when t is 0, we still have the same value, so A would have to be that. It depreciates more slowly. So if it depreciates more slowly, it's worth more after a longer period of time. That means we need to make this number, which is the number that's essentially bringing the thing down when you raise it to R. We need to make this number bigger. Like if it was 0.9, 0.9 to the 10 is bigger than 0.8 to the 10, and so therefore our value will still be higher. So we need to make this number higher. However, we can't make it that much higher. We have to keep it below 1, because if we made it above 1, then that would mean the value would be increasing all the time. Because if this was like a 1.1, 1.1 to the 10 is bigger than 1.1, right? So that would make the value increasing. So make it bigger, but don't put it above 1, and that would be fine. Question 8 then. Firstly, find R1. So we're going to integrate this curve here between this, which is obviously 0, and this. Now, where's this? Well, it must be at -2, right? Because of this bracket here. So it must be at -2. So we're going to integrate between 0 and -2. This here. I expanded this out already, so just expand these two brackets to make x squared. -4 plus 2 is -2x, -8, and then just put an extra x through everything, and we get this. And then, of course, we just integrate. We put the two numbers in. You can actually probably just get away with doing this in a calculator because it doesn't specifically say that you can't, and you get this answer here, so that's all nice and easy. The region R2 has the same area as R1. So we're going to integrate this curve between B and 0. And we're going to get this same answer, except when you do integration and the area that you're looking for is below the axis, by default, that integration will give you a negative. So while the size of the area is the same, the integration will give you a negative 20 over 3, because integration will always give a negative if the area is below the axis. So that's why I've set it equal to minus 20 over 3. From here, I'm just going to integrate as before. It's just the same thing we did before. Put the b and the 0 in. Of course, when you put the 0 in, everything just goes away, which is good. And then I think what I did was times this by, I think I times everything by 12 to make this here. And now this is quite interesting. Like the question is, how do you get from here to here? And, you know, the proper way is to show that maybe this has a, you know, that this has a factor of b plus 2. You can even do some polynomial division. And so you can factorize it and work out what's left and then do it again. Don't do that. Well, you can do that. That's fine. I did this differently. I just whacked this at the bottom of the page and then started expanding. So I expanded this b plus 2 all squared as b plus 2 plus b plus 2, which gives you this. And then I expanded again. I did this times this, this times this, this times this, and then this, and then this, and then this, and got me this line. And then I wrote up the page like so. And the examiner can't tell me that I'm not a complete genius here and didn't just know to, you know, separate, to randomly invent an 80b, the minus 80b from here because there are no b's here, and to separate this 8b cubed into a plus 12b cubed. And like, they can't tell me I haven't done this properly. Like, if you just read down, it does all make sense. It's legit crazy, but it does make sense. And you do get here. So I think I should be given full marks for doing that. But maybe if you have time, you might want to think about doing it a proper way. Anyway, when you solve this bit in particular, you end up with two answers. You end up with 1.225 and 5.442. Now, that makes b this. We know b is that because this is at 4, right? This bracket here tells us this root is at 4. So the 1.25 there is definitely there. The 5.4 is over here somewhere. And why is that a solution for this? Well, it's a solution because if you go far enough, like I said earlier, integration when you're going underneath the axis is negative. But if you go far enough along, like what you're trying to get to is to find a place where the area is 20 over 3, the same as it was before. And if you go far enough along, this massive positive area will be enough to cancel all of this negative area out and more, and end up in total with positive 20 over 3. Because this area is getting so big because this graph is rising so fast. So that second solution there is where this positive area is so big that it cancels entirely out this negative area with interest and gets you the last 20 over 3 in total that you need. And that's why that other solution exists. Here then, so the actual log law says that you do log of a divided by b here. But of course that just means a divided by b is equal to a minus b. You can times by b, you can move the a, b over to the other side, you can factorize an a, you can divide, and we'll get the answer here. The full restriction for b, now we already know b is positive, but you must have known that anyway because you're putting it inside of a log. So b has to be positive. But also, looking down here, a has to be positive, right? Partly because it says, and partly because you're putting it in log. But if a is positive here, this is similar to what we said earlier. If a is positive, now you know b squared is positive because it's something squared, and it's bigger than 0, which doesn't really matter, but you know it's positive. A positive divided by a positive is positive. A positive divided by a negative isn't. So this thing here must be positive, which gives you a restriction that b must be less than 1. So b therefore is between 0 and 1 for this to work. 10 then, prove from the natural numbers. That immediately means you should be thinking about odds and evens. So if n is even, you can write like this. You can then square it and add 2, which gets you that, which is clearly a multiple of 4 plus 2. So it's 2 more than a multiple of 4. So it's not a multiple of 4, right? It's 2 more than that. If n is odd, you can write like this. You can square it and add 2. You get this. You can factorize out of 4 from those two, and that's a plus 3. And therefore, this is 3 more than a multiple of 2. Sorry, a multiple of 4, which is likewise not a multiple of 4. So therefore, there are no numbers, whole numbers, natural numbers, where this is divisible by 4. Given this, the value is greater equal to that. Is this always true or not? Just try something. So I tried 100, and clearly this is much bigger than this. So okay, that's done. I thought about when does this equal this. So I just removed the mod and solved this in my head. So take away the x to get 2x, add this in, you get like 20. No, you don't. You get like 17 or something. Is it 17? No, 19. Sorry. You divide by 2 and you get 9.5, and you make them equal. So then I thought, okay, well, if this is ever going to not be true, if I nudge slightly upwards from 9.5, it's probably still true because I already have a case where it's true for a really big number. What if I edge slightly downwards? What if I try 9.4? And if you do that, you get this number and this number, which is less than. So I found a case just by finding the place where they were equal and then just nudging either side. The side that I chose first did end up working. So I found a case where it's true and a case where it's not. And so therefore this is sometimes true. 11 then, so we've got 6 minutes per kilometer for the first 4 kilometers, and then we start going 5% greater. 5% greater is, of course, timesing by 1.05. So the first 6 kilometers are going to be 6 minutes plus 6 minutes plus 6 minutes plus 6 minutes. That represents the first 4 kilometers. And then the 5th kilometer will be done 5% greater or slower, I guess. So we do this. And then the one after that will be 5% more than the one you did before. So this is how long the 5th took. And then you times it by another 1.05 to increase that by 5, because it's always 5% more than the previous kilometer. You get this number. Of course, this is not in minutes and seconds because this isn't. So you do 0.915 times 60, which will roughly convert to seconds, which is roughly 55 there. And we'll have the answer. This should be 36 minutes, of course. So I'm missing a 3 from here. But I think you get the point. Show that her estimating time for the whole thing is given by this. I had no idea what I was supposed to say in this question. But I essentially said that the first 4 don't follow any rule. They're just 6, 6, 6, 6. So then I said the 5th will follow the rule where it's 6 times 1.05 to the 1, and the 6th will be 6 times 1.05 to the 2, and therefore the rth will be 6 times 1.5 to the r minus 4, because this is 4 less each time. And I feel like that's probably enough. I think that's just what they're looking for. Anyway, estimate the total time it will take to complete the race. So we're going to have the original 24 minutes plus the sum of 6 times 1.05 to the power r, where r goes from 1 up to 16, because there are 4 kilometers done without this rule, 20 kilometers in total, so there must be 16 following the rule. And all we have to do is do this. I think I just moved the 6 out because I don't need it, and here, and then I, for some reason, randomly changed this to b. I don't know why I did that. I mean, I guess it's still mathematically correct, sort of. It's just a dummy variable, isn't it? But anyway, this is a geometric series, right? So the sum of the first n terms, this time 16 terms, is this. A is just 1.05 to the power 1, and r is 1.05, and of course n, like I said, is 16. So we should end up with this, I think. Looks good. We type this into our calculator, we get this. And then again, we do the minutes conversion thing here to work out this about 3 seconds. So it's 173 minutes and 3 seconds will be the time to do the race, which is actually pretty good going. It's pretty good. They should learn to pace themselves a bit better, but it is otherwise pretty good. We're going to differentiate this using product rule. So differentiate this one, leave this alone, differentiate this one, leave this alone. Looks a bit like this. Yeah, that looks pretty good to me. So we get this, and we're looking for a turning point. So f dash of x is 0. So I'm going to replace that with 0. We can factorize out I think I factorized out 2.5 and the e to the minus 2.5x here. I did. 2.5 times 4 is 10. Factorized out that, leave behind this. Now, exponentials can't be 0, which means this bit must be the bit being 0 for make this product 0. So we get this as 0. Add sine x, divide by 4. Sorry, add sine x and then divide by cos x, and you end up with what they want you to get. Sketch the curve this. Now, this graph is the same as this graph, right? When you're doing a modulus, all that happens is the stuff that was underneath the x-axis goes above it. So this curve here goes above it and looks like this. Nothing happens to this curve at all. This one ends up looking like this. Nothing happens to this. This one ends up looking like that. Nothing happens here. This one ends up looking like that. And the Marx team drew a nice graph looking a bit like this here. So that's the sketch done. The maximum height between the first and second bounce. Here's the first bounce. Here's the second. So we're looking for this height here. So of course, that's when the function has a stationary point, right? And we've already figured out the stationary points happen here. So let's solve this. Let's do tan inverse, and we get this. Now that will be the time of the first stationary point. So let's add, tan is repetitive every pi, right? So let's add pi, and we get to here. That will be the time for the second bounce. I'm working in radians, of course, because that should really be the default thing that you work in whenever you do these questions, although I think technically you could have done this in degrees. So we get this as our time for the second stationary point. We're going to put that into our height function. You don't really need these bars here because you're just going to type this into a calculator, and if it's negative, you just ignore the negative, and you have your answer. Explain why this should not be used to predict the time. Now, this graph, the stationary points, sorry, not stationary points, but the roots are all evenly spaced apart, which would not happen in real life. The bounces, the taller the bounce, the longer the time between the bounces, the shorter the bounce. These bounces should be getting closer and closer together, which is not happening. So just say something like that in words. Okay, how can I deduce Q is 4? This is not the easiest thing to do. You need to spot this bit over here. So x can't be minus 3 and x can't be 2. Now, I can see why x can't be minus 3, because if it were, you'd be dividing by 0 because of this bracket. So therefore, the x can't be minus 2 must be talking about this bracket here. So apparently, if you use x as 2 here, this becomes 0. So 2 times 2 minus q must be 0. Otherwise, they would just let me do this. And of course, that makes q equal to 4. So you can say something like that. Again, put what I just said into words. Show p is this. Well, if it goes through this point, we can replace q with what we just found out. If we replace, we know this point here, x is 3, y is a half. So we just put 3 and a half into here every time we see an x and a y. And sort this all out. This is 2, this is 6. 2 times 6 is 12, this is 9. And then we can cross multiply, and we end up with p as 15, which is what they wanted you to get. And now I think we need to work out this r here, so we need this point here. So that's when y is 0, right? When you've got a root. So we'll set 0 into this here. Of course, we know p is 15 now, so we'll put 0 into there. All of this is irrelevant. If you times by it, it just times by 0 and it goes away. So we just need that to be 0, which means x is 5. So we're going to integrate between 5 and 3. Of course, going to integrate this. This is not integrable right now. We need to do some partial fractions to make it so. So we're going to split this out. Put this here, and compare it with this. If x is minus 3, you can make this go away. So put minus 3 into here. Minus 3 times minus 3 is 9. 15 plus 9 is 24. Put minus 3 into here, you get minus 6 minus 4 is 10, or minus 10. Divide by minus 10, you get this. And then if you put in x is, 2 into here, that goes away. That becomes a 5. That becomes a 9. So we get a as this. And I've been unbelievably lazy here. I just put that 1.8 and that minus 2.4 in these fractions here. Don't do this. Your teachers will hate you. Just be normal and don't put decimals in fractions. You're not allowed to do it. I'm just doing it because I'm being really, really lazy and couldn't be bothered to write this out in fractions. It's just easier in PowerPoint to do decimals. So anyway, you integrate this. This has to halve because of this 2 here. Because when you differentiate this log, this goes on the bottom as it should here. But then the derivative of this is 2, and it times by that to make this. So I just halve this to make up for that. This one is fine, it just does that. Put in the 5 and the 3, and you get these numbers here. Of course, 5 times 2 is 10, take away 4 is 6. That's what I've done for this kind of stuff. Take away what happens when you put in 3, obviously. Expand out these brackets, you get this. 8 is 2 cubed, and so now I can bring that 2 to there to make 7.2, I think. Oh, sorry, that 3 there. 3 times this is 7.2. This isn't quite right. I can combine the 2's and the 6's, obviously. The log 2's and the log 6's. But log 6 isn't what they wanted. They want log 3's. Now, 6 is 2 times 3, so I can write this as log of 2 times 3, and then follow the log law. This is log of 2 plus log of 3, all times by 3.3. So I think that makes this. And then, of course, I can just do this minus this and just leave this alone. And I end up with that. And then it wants these as rational constants. So I guess A is 33 over 10, and B is, I think I just put 48 over 10. Yeah, it is. Of course it is. Just the laziest thing possible. So last question then, the curve is given by this. Find dy by dx at the origin. So that's when x is 0 and y is 0. Now, dy by dx, usually you obviously have a y here and an x over here in a function. But if you've got the x, you can just work out dx by dy and differentiate this normally. Because essentially the letters are just swapped around. So you can just swap around the letters here. So dx by dy, differentiate this with respect to y, put the 2 down here, makes a cos of 2y, because sine differentiates to cos, you make this. At the origin, x is 0 and y is 0, so let's replace y with 0. Cos of 0 is 1, so we just get 8. And then, of course, we can just flip this over to find dy by dx. So flip this over and we get 1/8. And that's that. Use the small angle approximation. We saw these earlier, but here they are again. So sine 2y is roughly equal to just 2y. So I'll say that, which means I can replace this sine 2y with just a 2y to make x equals 4 times 2y, which is 8y. I could maybe write that down as this. And now what it's saying is explain the relationship between this answer and this answer. Well, the 8th you can see is here, but it's also here, the gradient of this line. So you just have to say that this answer is representing the gradient of the line, which of course it is, because that's what dy by dx means. I feel like I'm missing something in that question because I don't understand why they bothered to ask it. But anyway, the last bit here, dy by dx, show that it can be written as this. So dy by dx, let's just flip this over then to work out that we've got this. So that's fine, so just flipping that over. Now, it wants me to write this in terms of x only. So how do we get this in x's? Well, we can start here, obviously, and this works for any angle, so I can just replace those with 2x's, and it will still work. And then I can take away sine squared, and I can square root, and I'll get this. And so therefore, if I take this here, and I square it, I get x squared equals 16 sine squared 2y, I think. Because what I'll do is I'll replace this cos 2y, just imagine these are y's, with this here. And then what I can do is I can go back to here and I can say, okay, well, if I divide this by 16, I get sine squared of 2y is x squared over 16, and I can replace that with an x squared over 16. And now this isn't quite how they wanted it. They wanted just x squared here. So I'll write 8 as, I think, I wrote it as 2 lots of root 16. Yeah, root 16 is just 4, so that's just 2 times 4 is 8. And the reason I've done this is because now these two things match. I can just put this 16 in here and say this is 2 root 16 minus this times 16, which is just x squared, and so I think this would be the answer. And that's the whole paper. Thanks for watching.